Buenas tardes. ¿Me escuchan? Okay, today I'm going to continue and complete these notes and solve some exercises. So we were talking about returns and estimate. Oh, I have my escuchan. I was talking about returns and estimating returns, and the goal being that we are going to estimate the appropriate risk-adjusted rate of return. That's where we're headed here. Okay. So what do we have? So we're talking about, well, we're using statistics now. I asked you to review statistics, and now we're going to apply the tools of statistics to estimate returns. And I gave you some information as ex ante data regarding two assets. Then we computed the measure of risk and the measure of return for the two assets and talked about which one we would pick depending on the type of investor we were, risk loving or risk averse. And the rational investor is assumed to be risk averse most of the time in many models, and at least the models that we discuss. But I have to also include a mention of the risk-loving type. All right, so here we left off looking at estimating not just the assets risk and return separately, but a combination of assets, because people hold assets at the same time in this case we call it a portfolio, right? It's a portfolio of two assets, and then we're going to generalize to the case of many assets. All right, so here I'm trying to see if anyone's joining me today. It looks like you're going to be watching this video after the fact, which is fine. It is an online course, a distance course. All right, so I talked about the variance. Okay, so let me go just a step back. So we talked about the expected return of two assets being the weighted return of the portfolio, and the weights correspond to how much will be invested in either of the assets. So using the information on the individual returns, individual assets returns, we are able also to get the variance of the assets. So I left off talking about the case where the covariance of the two assets was not equal to zero. If it was equal to zero, if the assets were not correlated, their returns were not correlated, then the variance would simply be this first two terms. Okay, so if there was no covariance between the returns of the assets, the answer would just be, I'm just going to write it here to be clear. I think I was being clear. Would be, let me grab it. It would be just these two. But this is only if the covariance of the assets, so they don't affect each other. There's no, or they're not correlated at any rate. Common variables or variables do not have an influence that causes these two to vary in any visible pattern, okay? So assets that, risky assets that don't covary are different from ones that do. So if they do covary, then their covariance is not going to be 0. So we have here the variance formula, and there's this extra term here, and I'll talk about where that comes from. And we spent some time, I calculated the covariance of these returns using Excel, and we got a negative, so they're negatively correlated. Well, we saw that if you remember back to the data, when you look at it, when A is high, B is low. When A is low, B is high. Okay, so they're correlated, negatively correlated. So what we're going to do then, putting all this together, we calculate the standard deviation. And what is remarkable is how small it is. If you remember back to the individual assets, let's grab this information here. So the individual assets return and standard deviation, this measure of risk was quite high. But now if you put them together, you hold them simultaneously, the fact that one is a hedge against the others of returns doing poorly, and vice versa, then you have a very low variation in returns. This is the standard deviation, is 1.22%, and that's all because of this term. Okay, so by creating a diversified portfolio like this, you can reduce risk. Let me see, I have slides down here. We did all this calculation. All right. All right, so what I want to say is, what if, before we talk more about diversified portfolios, what if you include more than 2 assets? What would be your variance formula in that case? Well, the measure of return, the expected return would be the same formula as here, right? This is general. This is for up to n securities. So you just keep on adding the weight times the expected return of each of the assets. But what about the variance? The variance formula looks like this. Now, what in the world is this? All right, so I'm going to lay out how you should think about that, okay? So what we're going to do, so we're going to take pairs of assets at a time. So we're going to look at the covariance of the weighted returns of A and the weighted returns of A first. Now, when we do that, when we say covariance of XA XARA and XARA, what are we actually doing? I'm going to move this over a bit. let's remember our covariance formula. So I'm going to grab the formula that you're familiar with. One second. From here. This is the example I like to refer to, because this is the one you spent time in your foundational statistics course learning. Hopefully you had your statistics course. If not, you're going to have to depend on what you're learning here. Okay, which is not bad, because I teach statistics, so it would just be what you would learn anyways. All right, that thing is happening to me again, or I have to post it here. And then copy. So this is the formula for covariance. So if I take this formula and I apply it to let x be XARA and let y be XBRB, move this up a bit. That didn't work. Nope. Okay, just do it with this. Oh, sorry, for the first one, I want to make XARA and XARA. What is that, in fact? So if I did this with ex post data, so historical data, just because it's a little easier to stare at, I think I'll do it this way. Oh, what did I do wrong? I have to put in the XARAs, right? Let's continue with that. I feel like I'm running out of space already. And like there's little eyes on here, right? There's like I'm going observation by observation. So if I get the mean of this, of XARA, I'm getting, oh dear, I'm gonna run out of space. So let me do it on another page. Let me do this on another page. I'm gonna copy this over to another page. I'm gonna go back. All right, so I want to use this formula to remember, what if I said covariance of XARA and XARA? What is that? So I'm going to do this one, and then we're going to reuse this result repeatedly. I go back and show you. Maybe I can grab the formula from here. So the formula that I gave you here doesn't have those weights on it. So that's another thing I'm showing you now. It's how to deal with the weights. So I'm going to put this X8 will be part of the weight. And all of these these all have eyes on them, right? Because I'm going observation by observation. I'm just not going to write it because it's going to look busy. And then what I do is I can, as you can see, I can factor out an XA from here and from here. So what this becomes is XA squared 1 over n minus 1 XA minus, sorry, RA minus ERA and RA minus ERA. So what is that? Does that look familiar? Does that look familiar at all? Okay, so the only thing that maybe you don't realize is doing this, right? So that you have to look at the covariance formula, the mean of X. So the mean of XARA is XA. So if you remember the rule for the means, the mean of a variable, a newly created variable, is just the, in this case, we're going to have the weight times RA is just the mean of the weight times the mean of the variable. So it doesn't change much. So this is maybe something you don't realize, but you should be able to see the pattern here that this is just the variance. This represents XA squared, and this is the variance of RA. So what I want to say, if I use my, so the same thing happens if I do this for ex ante data. In fact, the covariance of XA, well, I better write it like that. I'm going to write it like this again. Getting the covariance of these two will just be the weight squared times the variance of A. All right, so you're going to get used to seeing this. So look at that for a moment. I'm going to drink some tea. Now, you may or may not have learned this in statistics. Again, if you didn't learn in statistics, you're learning it now, so learn it now. So what I'm saying is then this term here, oops, this term here becomes the weight squared times the variance of RA, that I denote like this. But this one stays the same. Now I want to show you this method because I want to show you for 3 variables. But this is how we get the formula that we already know. So I'm going to use the formula that's already printed in the notes that we've already applied. All right, so this term, as I described, becomes XA squared variance of A. And this one becomes XB squared variance of B. And this one we can write as, just like I was able to factor out the A's, I should be able to factor out the A and the B. So these ones, this terms on the diagonal will become XA, XB, sigma B. sigma AB, sorry. Right? Because this is still covariance. It doesn't reduce to the variance. And this one will become XBXA covariance AB. Well, these are just the same, right? Because it doesn't matter if I multiply XA and XB or XB and XA. Those are the same number. So there's two. So that makes two of them. And that's where the formula comes from. So that's, you have this because that's the covariance of A with itself. This is the covariance of B with itself. And then these are the two added. So let's look back at that formula so you can see it where it comes from. So there it is, right? This is the formula for variance that we used. So this is for two variables. This is for two assets. XA, XB, and then two of XA, XB, and sigma AB. All right. So now let's do it for three. Let's see who's here. Anybody joining me? All right. Okay, so I'm going to do this now for three variables. So let's do the variance of RP where RP is XA, RA, so one asset, asset A, and then a second asset, B, and then a third asset, C. So let's make that table again, but a little bigger. And so what do you think will be the formula for that? Let's remember this one for two and the method that I used to describe where it comes from. Should the variance of three variables have a 3 in it or not? Maybe that's the way to ask. How is the third variable included? Well, the way it looks like it appears, it's not exactly clear from just looking at two variables, but once I handle three variables, you'll get the pattern, right? Because with two variables, it looks like I have to take two at a time. That's in my matrix. I only can take two at a time. So this one, as before, will become XA squared sigma A squared for the variance. This one will become XB squared sigma B squared. And this one will be XC squared sigma C squared. So everything in squares. Now when I go to these two, I'm going to do the same thing, the covariance like we did before. So it's the same result. It's going to be XA, XB, covariance of AB. And this one will be XA, XC, covariance of BC. And hopefully you're seeing the pattern now. So I'm going to write this one, even though B comes first, I'm going to reverse them because I can do that, putting them in alphabetical order. XA, XB, sigma, AB. And then this one over here is going to be XB, sorry, XB, XC, sigma, BC. And so we're starting to see, we only have a few more to put in, but already you should see that there's two of these. And then there's going to be two of these. So there's going to be one right here. That's what I'm going to put in next. So this one will be XA, XC, sigma AC, and this one XB. So stick with the alphabetical order. XB, XC, sigma BC. So what do we have? These are the same. No, what did I do wrong? I wrote a B here. That's a typo. That's AC. No one here to stop me. I made a mistake. That's an A. And so those are together. All right, so there's two. That's how they pair up. So the matrix should remind you that I'm working in pairs. So what is the formula then for two assets? It's going to be each one has the weight squared times the variance, and then I add two of the covariances in pairs one at a time. So my final formula will be variance RP, the return to the portfolio, would be XA squared sigma A squared plus XB squared sigma B squared plus XC, so it's very long, B squared plus XA XB sigma AB plus XB XC sigma BC plus, oh, and I have to say 2. I forgot to say the 2. Let's do that again. And then 2x AXC sigma AC. Very long, but it's easy because there's a pattern. Once you see the pattern, you can handle this. So you have quite a few things to compute to get the variance. All right, so where were we? So we were on this page, and I just described what this formula implies. Use a matrix to find the variance of up to n assets. Okay, so I just did it for 2, I did it for 3, and you can do it for 5 or 10 or 1,000. Obviously, you want to use a computer or some programming software to do that, and that's what exists. Or you can program it yourself. So, what did we learn? We learned about the effect of diversification on portfolio risk. When we put assets together that are negatively correlated, we succeeded in reducing its risks. So much so, it's smaller than if you were to just average the variances of the assets together. It's very small. So the variance of the portfolio, let me go back, we got, it's down here. No, it's on the next page, the top. The variance was 0.00015, and the standard deviation was relatively very small compared to the asset standard deviations themselves. So the question becomes, what's going on? Okay, so can I just add a whole number of assets together and continually, to diversify the risk, to eliminate risk? Can I do that? Well, combining two assets, we eliminate some risk, mainly due to the covariance. Using diversification, this is a strategy designed to reduce risk by spreading the portfolio across many investments that have a negative correlation, right? Now be clear, there's two types of risk. The unsystematic, unique, or asset-specific risk can be diversified away, as I've shown you. But market risk can't be diversified away. So if we were to look at, and this has been done, a well-diversified portfolio that was created, or let's call it a portfolio that was created by randomly combining 20 risky securities. So let's say this was done. This was done in a study years ago, and it's been repeated, okay? And it demonstrates that randomly choosing a number of assets. So this is showing, okay, just one asset was chosen from a database, and all the returns data was used to compute the average annual standard deviation, okay, and it was 49.2. It could have been any number, but just for one asset. But then we combined, you can combine 10. Okay, let me do this again because this will be clear. All right, so if I took the information on one asset and I repeatedly did that, that's what this is. I'm going to repeatedly sample one asset. On average, looking at the returns and the average of the returns of each of those single assets taken, the average is 49.2% in this study. What if we took 10 and we repeatedly sampled 10 assets? And we had returns data on them, historical returns data, and then calculated the standard deviation for each and averaged those. So for 10 assets at a time, and then 10 assets at a time, and each time we select, they're randomly selected. So with repeat sampling, we repeatedly sample and calculate the standard deviation of that portfolio using the formula that I showed you. The average standard deviation is almost half, right? It's much lower. Well, it's half. And then repeatedly doing the same thing for 20 assets at a time, it's even smaller. But beyond about 25 assets, there's no more benefit of randomly or selecting many assets at a time. You're not able to reduce the standard deviation of the portfolio just by randomly choosing. So this demonstrates without, there's no logic in picking this, just randomization. Now, obviously, if you use some sort of logic, you may be able to go down, not logic, but I mean considering their correlation or their covariance and picking them in a certain way in a portfolio, you may be able to diversify, but not any more or not any better than being left with the non-diversifiable risk. So this is showing, this is done randomly, but there were several samples, and that's supposed to mimic, it's supposed to mimic the best you can do, okay, in picking assets. And there's still a remainder of risk, and this is attributed to the economy, okay, and the risk inherent in investing in risky assets. So what we say then, it's not a matter of how you choose the assets alone and combine them in a portfolio. You have to think about how they're correlated with the economic returns in general. And how do we measure economic returns? Well, we use as a measure, as I've shown you before, the S&P 500, the index of the top performing risky assets is used as a metric to observe the state of the economy. So here we have in this table, this is the return to the S&P 500. This is an index that combines the top performing 500 stocks at any point in time and puts them together in like a weighted average, right, of returns, and then monitors it historically and comes up with, well, I guess historically and then prospectively, and comes up with this index. And we're not going to talk too much about how it's computed, but this is the number. In a good state of the economy, 18% return is relatively high. All right, so we saw that the on average over 100 years, practically, well, I guess 80 years in the stock market, on average over all those years, despite depressions and recessions, there's a 12% return. So 18% is relatively higher than that. In the poor state of the economy, 6% is the return. And how does this stock perform? BCE company has even higher return when the economy is doing well. And unfortunately, when the economy is doing poorly, it has a negative return. So what does this reflect? It shows that there's a relationship that is, there's a correlation, right? And that there is a relationship. Like, I only have 2 data points to make this simple. I need more data to be sure. But as it stands, we find mathematically, we can solve and find that there's a slope relationship between these two. So there's one point, the good point, and this is the poor point. And because there's only 2 data points, we can imagine a least squared regression line that goes right through them, even though, again, this is not the best idea because it's just 2 data points. But to make my point, we like to measure the sensitivity of BCE's returns to the market returns. Remember, I promised you that we were going to use our statistic tools, and I focused on making the market returns X and the firm returns Y for a reason, right? So we're going to read this as the sensitivity of the firm to market returns. In general, when there is a correlation, we can't attribute cause, but looking at financial statistics over time, there's a theory inherent or a theory derived from there that insinuates that firms are influenced by market performance. And this is a proxy the S&P 500 is a measure of that, the market performance. All right, so if I calculate the slope of this relationship, I will get 2.5. So how do I do that? I do this by change in y over change in x. And the change in y is from here to here, right? So let's say I start here and I end up here, or no, let's do it the other way. If I start at a -4 and I end up at 26, so let's look at that first. The change in y from point to point is what? Are you there? So you're going to take 26% minus -4%, and you're going to divide by, so starting again with a higher point, 18% minus 6%. And you get 30 over 12. Which is 2.5. And I don't use the percentage because I had percentage on the top, percentage on the bottom, and they cancel. So this is just an index. Okay, so BCE is the beta, the slope with Greek letters, is an index. And how do we interpret that index? We say that following a change of 1% in the market, we'll look at the positive, the returns on BCE will change by 2.5%. If the market does poorly, if there's a negative return, so there's a loss in the market for every dollar invested, then investors in BCE will have a negative return, negative 2.5%. So this is seen as quite sensitive. Okay, so a 2.5 beta is quite sensitive. I'd like more data to establish how good an estimate this is of the relationship. But in general, the covariance is negative. The covariance is positive, right? Because you have a positive beta. And we did say that remembering beta is equal to, if you remember our formulas, the correlation, the sign of the correlation is the same as the slope. Okay, so the correlation is positive. It's just that this is very sensitive, and that's what's picked up at the 2.5 measure. So this is just saying if the covariance of returns are negative, though, BCE, the beta of BCE will be negative. And that's because correlation, remember, is computed by covariance, standardized. So these are, now this is your opportunity. If you've understood and followed the stats review, you're going to apply what you learned. If you didn't understand the stats review, you have to learn it to understand this, or you're going to understand it somehow. At any rate, you're going to have to understand the stats review. All right, and that's what I say here. So we write where the market portfolio is a portfolio of all assets in the economy. We use the S&P 500 as a broad stock market index to represent the market. And the beta is the sensitivity of the stock's returns to the returns on the market portfolio. And I just rewrote all these formulas. This is the extra formula that I want to talk about. So this is just the slope. I'm just going back here. So where does that come from? Remembering our formulas. We talked about this is the slope, the formula for the slope when data is historical, and then we use Greek letters for when data is ex ante. Sorry, I'm gonna make you dizzy. And then what I explain is in finance notation, I put in, so it's the same formulas, but just in finance notation that I come up with showing you that I is for the asset and M is for the market. So this formula is just from your basic statistics course, but I've used the variables of returns to an asset I and returns to the market portfolio S&P 500 as an example. So where does this last formula come from? That comes from, and I did explain this in the stats review, that comes from substituting this into here and canceling the standard deviation of the asset return. So it shows that the sensitivity is calculated as the covariance for every unit of variance of the market portfolio. So those are the two forms. So why do I have two formulas here? Well, sometimes it's easier if you just have to make two calculations than three. You'd have to make three calculations to find the beta over here, and this just takes two. Also, it's the interpretation. It's a nice interpretation that we spread out across the covariance per unit of the variance in the market portfolio. All right, so what next? So what next is the capital asset pricing model. So this was our goal, to get you here. Everything you've learned so far in this course is to get you, well, anyway, there's still more to learn, but to get you to one example of a model that can be used to estimate the appropriate risk-adjusted rate of return. Okay, so these are this is the setup for the model, right? And you have to know the assumptions to fully understand the model. So let's see if we can review those. All right, so M represents the market portfolio. So to this moment, we've been using S&P 500 as an example of market portfolio. So inside of M, the market portfolio, are a fraction of all risky assets that exist. So all securities are in M, and all investors have M in their portfolio. So they have invested in a well-diversified portfolio that mimics the market portfolio or the market portfolio. You can actually invest in an index that tracks an index like the Dow Jones or the S&P 500. And there are other indices created by other firms or investment companies that will do the same. So you can invest in that and get a return for every dollar invested in that index. All right, so all investors have M in their portfolio since they are all investing in the risk-free asset and the market portfolio. So all investors are going to invest in risky assets and in the market portfolio. This is the model, okay? So remember we said that I explained that the T-bills, these are 30-day bonds issued by the federal government that on average, historically, do better than inflation. So it's a way to protect against inflation or hedge against inflation. So any investor, rational investor, will invest in risky assets, risk-free asset, and a portion of their investment will go into the market portfolio. All right, so having said that, investors are only concerned with the return, the average return on the market portfolio and the standard deviation or the risk of the market portfolio. And with the contribution of each security from any firm one at a time, we're going to take firms one at a time. So that contribution of the risk of some firm you're thinking of adding, or an investor is thinking of adding to the portfolio, and its influence or its the impact it has as a result of the market returns. So the contribution of systematic risk is going to be measured by the beta, and we're going to also look at the contribution of the expected return. So what we are going to focus on here is estimating the return, the expected return for this firm, the returns to the firm. And we're going to do that by saying we are, as investors, the return expected for firm I should be over and above the T-bill rate to compensate for the market risk premium let's see if I can using the market risk premium. So this is the market risk premium, remember, and this is the risk premium, but this is the market risk premium, because here, if you remember back to our review of returns, I taught you to calculate the risk premium, but in particular, this is the risk premium because it's the expected returns to an asset minus the risk-free rate. So to be incentivized to hold the market portfolio, investors are going to expect a return over and above the risk-free rate. So this is the risk premium, but of the market portfolio. So we call it the market risk premium. So for every unit of of risk measured by the beta, so this is the contribution to systemic risk, you want to be compensated to hold asset I, you want to be compensated by the market risk premium. So for every unit, you want to be compensated. So if this is 1, you want to be compensated the market risk premium. So essentially this will be 1, and then this RF will cancel with that. And so basically, if an asset is just as risky and in its returns as the market portfolio, then the expected return on that asset should be equivalent to the expected return on the market portfolio. All right, so this actually makes a line. Okay, so this is a line. And I'm going to ask you to think about, what is the slope of this line? So what's going to happen is this is going to be your variable y. So when I draw this, I'm going to put oh, this is a terrible drawing. Let me just show you what I've got. So there, it's on the next page. So here's my line. Now, as I promised you, if the beta is 1, putting beta here, an expected return there. In this way, I map risk here and return here. So I'm showing the trade-off between risk and return. And when risk is 1, measured by beta, the expected return for an asset should be the same as the expected return to the market portfolio. So this is here. The risk-free rate, this is its return. So it has no risk. So that's why it's here. This is 0. That's 0 right there. And my question to you is, what is the slope of this line? This is called the security market line. All assets fall on this line. Given the assumptions of the capital asset pricing model, all assets fall on this line. So there's the T-bills, there's the market portfolio, and then any other thing that exists in the market will fall in this portfolio, and we'll talk a little bit more about that in a bit. So my question is, what is the slope of this line? Right, so what's the slope? All right, so some students might think that this is B, this is the slope, but no, that's not the slope because the B is here, it's the axis. So that means that this must be the slope. This is the y-intercept. Let's look at this together. Let's say when y, we're just going to say y and x because these are very long labels otherwise. So when, do it backwards, x and y. So when X is 0, what is Y? So X is beta. So when beta is 0, this is 0. So Y is just RF. So this is the Y-intercept. Right here. And so that's like A, right? In a line. And then this is your X variable here. And then this must be your slope. Even though we call that beta, but we put it on the chart here. All right, so this is my slope. So you can see that here, to go from here to here, change in okay, so I don't know why I can't do this nicely. Let's just leave it like that. So if this change here and this change here, so changing Y would be expected return minus RF, and the change in X is this 1. So you can see the slope. Okay, so that's the slope. So you can imagine for 1 unit, change in risk, the investor expects the market portfolio. All right. So this is basically the capital asset pricing model. So let's see if we can apply it. If you didn't understand a thing I'm saying, let's just see if you can apply it. So here's an example. We have information on asset A and asset B, and we want to apply them, combine them into a portfolio. Combining them into a portfolio, we have information on their beta, the sensitivity of A's returns with the market portfolio and the sensitivity of B's return with the market portfolio. So B is more sensitive, right? And using the capital asset pricing model, let's calculate. So this is all the information I'm given. This is it. I don't have returns data. I can't calculate an average. This is all I've been given. With this information, I'm going to assume the capital asset pricing model is a good model. So I'm assuming its assumptions are in effect. And I'm going to calculate the expected returns. So using the model, it's RF plus the beta of A times the market risk premium. So we get all the information at the top. So the market risk premium is 10% because I get that from doing the calculation up here. So the expected return to asset A is 12%, given only information captured by its risk, measure of risk, because all that matters is its contribution to risk in the market portfolio. So did I do that right? Because this will be 0.08 plus 0.04 is 0.12. And then the same thing here, I'm going to put RF as 0.04 plus beta B, which is 1.2 times the market portfolio. Sorry, the risk premium, market risk premium. And then this is going to be 16%. All right. So this is a new way of calculating the expected return to an asset, and it's done using the capital asset pricing model. I didn't go through calculating the average return over time. I'm interested in its relative contribution to risk to the market portfolio. So this is going to be my measure of expected return, a required return, let's call it like that. Okay, so these are the required rates of return. All right, so if I'm to combine these now into a portfolio, 60% invested in A and 40% in B, the expected return is a weighted average of those two. And I could also calculate the beta of that portfolio as a weighted average. So we are computing a weighted beta just like a weighted return. So this is new. And this is possible all because of the architecture of my security market line. So what I've done is I picked two assets around here. The one's lower than beta equal to 1 and one's higher. And then I combine them. When you combine assets, so if I have two assets here and all assets fall in the line, given my assumptions, then they will, any combination of them will also fall in the line. Now ours doesn't fall exactly here. The beta is not 1, but it is, it's just under 1. Okay. So the portfolio will also be on the SML. All right, so there it is then. I finished these notes. You can work on those exercises. There's a second part. Give me a second. I just want to check how we are in terms of timing for your last test. Oh, we're good. We have good time here. All right, so we're going to keep going to finish this material. There is, let's see if I can pull up. Yeah. All right, so what we've done, so what I've taught you are this set of notes. So I'm going to open up, I think I opened it all up, but let me check. Maybe I'm wrong. So you were supposed to have completed this already, but yeah, I have everything open for you. So there's a number of exercises. I'm going to have to reload this page. Okay, so sorry, I'm going so fast. So here's all the material. All right, so you can solve all of these. Next class, so Wednesday, I'm going to work on this material here, cost of equity, and finish so that next week you can have your test on May 3rd, which is on the Wednesday, I believe. Perfect. Oh yeah, we're in good time, but you have to practice. So yeah, so Wednesday we're going to finish this. And then you're supposed to work on all these reviews. And so we'll have Monday still to do review. And that's it. So any questions, please email me. The test will still be on May 3rd. And it just, well, I guess it'll be online. And then we still have a week to do. I'm very surprised, like we're actually getting through this stuff, but let me know if you guys think I've gone too fast, or I mean, I'd like to stick with the schedule. I don't want to change the schedule. So just let me know if you need any help. We can have a virtual, well, we have a review session, but you need to show up. So hopefully you come on Wednesday or Monday for the review. Okay, so Wednesday will be the test. Let's see, should I do something here? Let's see. Oh, lots of problems to practice. Well, I'm going to leave them for you to work on. Where I'll start on Wednesday is with this review. I'm going to do some of these exercises. So if you can prepare them, that would be fantastic. And we'll talk about that. Yeah, so I'll start with that a couple of questions from the review, and then I will finish the cost of equity notes. All right, so I'm going to sign off unless someone is here to ask me a question. Okay, have a great rest of your day, and keep me posted. Talk to you soon.